Now this map is a marbleized and planetized star map that points up the fact that the universe is in motion. We've captured the galactic flow in the star map and the liquid flow in the old bookbinding craft of marbling, floating paint on water and swirling it around. And the two combined, the galactic and the liquid, point up the universal flow. Each one is different, an object of art and star map at the same time. We've arbitrarily added these little planets to give it more artistic effect. My friend, the master marbleizer, Count Fabriano, will come here very soon, and we can get a picture of him and have him describe how he's been working on a book describing all the forms of marbling in nature, which is in the rocks and the flow of the sand and the water and the beach and the turbulence in the air. Flow of the galaxy and the flow of the star map together combined to make this. Each one is different. Every star is precisely plotted, but the marbling is all flowed. But of course, everything is at random. That's why the universe is in motion. Nothing is standing still. Everything is moving. And my friend Count Fabriano, who may appear soon, the master marbler who has been doing this for many, many years, does it primarily on fabric. And this is a color Xerox of a piece of fabric that has the marbling on it. And we're standing in front of monster marbleized. There's I am, and there's Count Fabriano with a NASA T-shirt. Here I am with another marble map. These are what we call the monster marbles. And here's a close-up of the monster marble in a detailed version. Get another example of it close by there. He should be coming very soon, and so you can get a personal meeting of Count Fabriano. Here are books that are marbled in the front and back covers. And different techniques of marbling, combing and spreading it out, and he can give you a better description of that sometime when we get him here soon. And these are all examples of the marbling art, but this is wooden marble. This is the blind man's tactile heavens. The wooden panels with upholstery nails as the stars so that a blind person could run their hand through the Milky Way. I built this for the 400th anniversary of the birth of Kepler out in the woods. We're here at the Dynamic Graphics Corporation on the top of the Great Western Building in downtown Berkeley on this December 8th, 1979. And we're creating here today a map of the universe that's going to be about 137 inches long and about 60 inches high. And I'm standing right next to a map that I made a number of years ago, and the computer drew this map in one piece in 1 hour and 45 minutes, with every nuance of brightness reflected to hundredths of a decimal, more star names than any other map, all the Greek designations, and every area has precise visual brightness to as much as it's taken by what they call photoelectric photometry. This is like taking a light meter reading through the telescope. And these particular coordinates are from the Yale Observatory's Bright Star Catalog, and I've revised and refined and developed this map in these 9 years since I published this first one. And now we're going to go down the hall in this graphics laboratory and see some later editions. This next map is the world's largest on a single sheet that has the extreme limit of naked eye visibility. This map right back here has 5,700 stars. That's 6.1 visual magnitude, which is the all essentially naked eye stars. Not stars that you can see them through the telescope, but you can see a lot more through the telescope. And now we'll come down this long corridor atop the penthouse here and see what I call a giant map, 9 feet by 4.5 feet with 8,602 stars, and every one of them designated, and again, all the nuance of brightness. Now the computer originally drew this map 25 feet by 12.5 feet. This is a 37% reduction of the original. And if we'll keep going down the hall, we'll see a half-size reduction of the original 25-footer. This is Sirius, the brightest star, the belt stars of Orion, Betelgeuse, the shoulders of Orion, Taurus, the bull, the Hyades, there's the Pleiades, or the Seven Sisters, Castor and Pollux, Gemini, the twins. They're all on there. These little numbers here, I don't know if you can see them or not, they're what they call Yale Bright Star numbers. They're listed in the Yale catalog from number 1, but in order of right ascension, coming this way. So we pick a number here, there's 3,657 stars on this side of that star, and they keep increasing going this way. The Flamsteed numbers are these numbers within a constellation that are numbered the same way going that way, but starting with number 1 out here, and there's 20, 51, 81, 90, 95th star of Leo here. Leo Minor, the 21st star, and so on. Here's the Big Dipper. Can you get up to the Big Dipper? It's the Big Dipper that goes on and points up to the north. This is a cylindrical projection which stretches the northern and southern hemispheres so that if you look at the top at an angle, like you're doing now, you can see them more or less in their true perspective. This is the Southern Cross down here. We can't see that Southern Cross from our location here in Berkeley, California, but when we get down the hallways, I'll explain how the stars are seen and how the coordinates are used for navigating and finding your position on the Earth. Come this way now, down the hall, and we'll check out the monster star map. And this has 25 separate sky areas. It's 12.5 feet by 6.5 feet long. And every one of these 25 areas has its number of stars. There's 572 stars here. There's 459 stars here, totaling 8,602, the same as the giant map. And every fifth of a degree so that you can pinpoint your exact plot in the heavens. This line here is the ecliptic, or the path of the Earth projected into the sky. It's also known as the zodiacal path because there's the zodiacal constellations: Aquarius, Capricornus, Sagittarius, Scorpius. This is the summer triangle: Vega, Deneb, and Altair. It's now in the December sky in the west, and on Christmas Eve, of course, in the northwest, you can look up and see the Southern Cross, or the Northern Cross as it's called. It's actually the wings of the Cygnus the swan, the tail of the swan, and the head of the swan. And Vega, one of the brighter stars in the sky, Lyra the lyre, the harp of Apollo, Hercules, Corona Borealis. There's Delphinus the dolphin, Aquila the eagle, with Altair, the next brightest star in the summer triangle, and it's flying this way. Antinous, the little boy riding on the wings of Aquila the eagle. This is an ancient asterism. So on this map I have all the old constellations that have been discarded. The International Astronomical Union that dogmatically set all the constellations threw out a number of them, like Globus Aerostarchus, the air balloon, Phenacopterus here, the flamingo, the bull of Poniatowski. This is a miniature Taurus, a little V shape for the head of the bull and little horns up here after the Polish king. Cerberus, the three-headed dog, is actually the hand of Hercules, the giant, the kneeling giant. Now let's keep going down the sky here. Is the head of Hydra, the sea snake that runs all the way back there. Castor and Pollux, Gemini, the twins over here. And it's right into the wonders of the so-called wintertime sky. Everyone talks about seasonal stars, but it's more or less a misnomer because you can see most all the stars you can see in one night's viewing if you stay up all night and watch the stars from sundown till sunup. When they mean seasonal stars, they're talking about just the first few hours of evening after the sun sets. And the wintertime stars right after sunset are the Orion the Hunter here, the belt stars that are pointing down to Sirius and up to Aldebaran, the eye of Taurus the bull, or the Hyades, the half-sisters of the Pleiades, which are the daughters of Atlas. Here are the horns of the bull, and Capella up here, the goat star. This is Orijah the charioteer. Anyway, these are some of the stars that are in the sky, and we'll continue on our journey here into this. Come this way. These are small maps, mock-ups, and tests of the computer map that's being drawn right now. And in just a few minutes, we'll get in there. It has the curved north and south borders, so that it is more not stretched as much as the rectangular maps. Now at the end here, this is all the stars with just circles, and this is the brighter stars for the whole map. There's the belt stars of Orion down to Sirius, the Dipper arcing to Arcturus and down to Spica and the Southern Cross, and Rigel, Centaurus, and Hadar pointing to the Southern Cross, and the summer triangle here, Vega, Deneb, and Altair. Now we're going to come into what I call the Holy of Holies, the computer room where the machine is actually creating the universe. But before we go in, I wonder if you could turn and see this map here. I wanted to make a brief statement of how the stars are seen and how the coordinates are used. These coordinates here are based on the Earth's equator extending into the sky. So whatever your latitude is, that's straight up overhead. Directly over the equator is the celestial equator. Now here in Berkeley, we're about 39 or 40 degrees north, so this line here is straight up overhead where we're standing. And whatever your latitude is, that amount of degrees off the poles is what you always see as north circumpolar, and that same amount off the bottom up is what as your southern horizon. So we never see this 39 degrees. We always see this 39 degrees, and everything in between here rises and sets in an arc across the sky once around the whole map every day. Now wherever the sun is on the zodiacal path, it's approaching now the December solstice, December 22nd, where it's the shortest day. The stars on this half of the map are the early evening stars, and stars on this half of the map are the early morning stars. So as the sun goes this way, you see a few more stars each morning and a few less each evening. Back here in September at the autumnal equinox, this half was the early evening stars, this half was the early morning stars. Now, if you were at the equator, you'd see the whole sky. The poles would be on the horizon, and the whole map would rise straight up overhead and set straight down. And you'd see the whole sky at the equator. Okay, now that I've whetted your appetite, we will now come into the computer room. Okay, we're in the master control room now, and I'd like to introduce you my computer programmer, who's the brains behind the machine. This is John Wells. And now we're going to look at the actual device that creates the heavens. And now right over here is the computer readout, the digital readout. All these little numbers tell the plotter where to go, where to draw the stars. And each one of these areas is what they call a buffer. That's right. Right. And it collects that much data and then goes on to the next, and after it's collected that, it starts drawing on this machine right over here. Okay, and we'll come right over to this is the plotter that creates the stars. And this machine is actually now drawing for 4 hours just half the sky, the southern hemisphere. And it's just about ready to draw the Orion's belt and the brightest star Sirius. And maybe we should open this up so that we can see this. Can I open this up? Okay, we'll just open this up a little bit so that you can see the machine drawing it. Now the XY coordinates, or any drawing, you know, like those little slates that you can turn one way and turn the other way, well this, the paper moves and the stylus moves back and forth to get your XY coordinates to draw any picture you want. And we're just coming up now on Orion. And this can do multicolor drawings and with what accuracy? What's the accuracy on it?
1/1000th of an inch. This on the back wall was produced by this plotter using ballpoint pens, 4 pin colors. And that's an actual original off of the plotter itself.
Okay. Now we'll close this down here so that the air doesn't get to it. This room that we're in, the noise you hear is the air conditioning and the coolant of all this computer equipment that we've got going here is the prime computer, storage tapes. And if you look at this is one of the most amazing things that I have come across. This table here that draws these contour maps. Here's either a satellite or surveyors go out and measure these. And all these lines on here, this little device, you just run it across there. Underneath is sensitized, and the digits go right through this cord into the computer over here and is stored. And all I have to do is just put it on this machine, and the whole map is drawn just like that on the computer. Now, the president of this company, Dynamic Graphics, is right here for us to learn about this machine that actually makes the contour maps that I tried vaguely to describe. Now, how does this thing work anyway? This table with the contours and underneath and...
Okay, this is a table. This machine is kind of the inverse of the plotter.
You have the map that's already drawn.
We have a map drawn, and there's wires under this table. There's a little magnetic coil under this cursor. And as you press the button, it can, within 0.005 of an inch, measure where the little crosshairs are located on the map. We can take and read the locations of contour maps along the contour lines and find out the XY coordinates along the contour lines. We can enter in over on the keyboard the elevations. Given the locations and the elevations, we can have the computer develop the shape of the surface represented by this contour map. Mm-hmm. We then do another contour map that shows the contours after they've done a development and they've cut away dirt and added dirt. And then for each area we can tell the number of cubic yards taken away or added.
Yeah. So, but it looks just like the Marbleized map. If I took one of my marble maps and put it on there, we can actually draw the marble.
These are all lines of equal height. Okay. Once we've entered the surface definition into the computer, we can have the computer draw out its own contour map. And we can have the computer make a pictorial representation of the shape of the surface.
Very good. Now, I think the machine is coming right up on making the brightest star Sirius, so you can actually pan right over here and start watching it happen, which is going to be very soon now. And you can come closer. We'll open the box. I'm going to step in front of the camera, if you don't mind. Excuse me. Thank you very much. And
Don't hit those buttons.
oh, no. I won't. So we're going to open this up now, and or shouldn't it be open while the Sirius is going on?
Okay.
And now we're going with Sirius, the brightest star, and see that thing going around and around, and it's filling it in, filling the dot in. And now the magnitude of the Sirius is minus 1.45 visual magnitude, and the minus numbers are the brightest, and the plus numbers are the dimmest, like nail gauge, is the way they go. And for each jump in magnitude, it increases about a little over two and a half times as bright. And of course, every time you double them or increase one magnitude, it doubles the number of stars. And this is now Sirius is drawn. Now there's another star that's being drawn. It's probably right on top of it that we can't see. Maybe it's the companion of Sirius, who knows. And pretty soon, it'll start drawing the stars of Orion, which on this half of the sky will be all the belt stars. The top belt star rests just very close to the celestial equator. There's Sirius, the brightest star, and I'll show you the way it looks on this map in here. It's the brightest star there. The belt stars of Orion point down to it, and in just a few seconds well, actually it isn't, because that's about 10 or so minutes away to get into Orion by the computer. And
You'll notice the way the stars are being plotted on this. It's moving back and forth, and the order of the stars has been chosen so as to minimize the amount of travel time in the plotter pin from one star to the other. And if you were to do them randomly, of course, you would spend a lot of time on the plotter traveling from one star to the other. So the stars have been what I call strip sorted, so that it minimizes the amount of distance it has to move from one star to the other.
All these stars are from the Yale Bright Star Catalog from the Yale Observatory, and of course they rely on other observatories, let's say in the southern hemisphere, to bring their collection of coordinates together and publish their list. Other observatories have their own lists, some publish, some not, and we're using the Yale. There have been books written about the accuracy of various catalogs, and Yale doesn't rank near the top, but more and more uranographists, people who graph the universe, are using the Yale catalog, because essentially for star maps we're interested only in the naked eye sky, the stars that ordinary people can see and to use to find their way or to stargaze or to learn the constellations. And my whole interest is the star lore that the ancients, you see, we're seeing living history itself. When we look out into the sky, we're seeing what the ancients saw. And so I'm primarily interested in all the naked eye stars. And this is almost the extreme limit. That one that we had out in the hall there, what I call my award-winning map, I entered it in a map design competition by the American Congress on Mapping and Surveying, and along with my award-winning was the CIA satellite map. Oh, the next brightest star. You can just pan right over here for a moment. That's Canopus. It means the chief pilot of the fleet of Menelaus, which is in the ship Argo, the ship that carried Jason searching for the Golden Fleece. The whole constellation of Argo, the ship, was broken up by the Astronomical Union into three: Pupus, the poop deck of the ship; Corinna, the keel of the ship, which Canopus is a part; and Vela, the sails of the ship. But on this map here, as I say, there's 5,700 stars. There'll be well over 6,000 on this one, and on the monster map that we saw earlier has 8,602. That's the extreme limit of naked eye visibility. Now that we've seen this computer in operation in the room, I'm going to go out and summarize and see what we've done in our operations today. We come back to our award-winning map right here, which is the first computer map I drew back in 1972. And all these maps are representations of the celestial sphere. Unlike terrestrial geography, where we must go to the spot on the map to appreciate it, with a celestial map, you can be any place on Earth and the stars just come to you. You can stay put, and one night the whole sky will roll around, especially at the equator. But all these are flat representations of a sphere. And you, no matter what you do, there's always going to be this distortion either in the top or the bottom, or if you make another projection like the spherical ones, it'll give you a distortion another way.
Sort of like a Mercator projection versus a
Yeah, this is like a Mercator,
draw.
but this is a straight cylindrical with each degree being equal. Each degree is equal both in latitude, or what they call declination, and longitude, what they call right ascension. No matter what representation you make, a flat surface will always make some distortion. And this is how I got started in celestial map making to begin with. Came home from the 1970 eclipse and found that the National Geographic put out a circular star map, what I call made for people that live at the North or South Pole. The poles were centered, the circumference was the equator, and you have to piece the equator together in your mind to get bearing, and anybody in North America looks out, the equator is halfway up in the sky. So everybody knows what's in the north because they can see it anytime they want to. It goes round and round. But when they look south, they miss all this beautiful stuff, the flow of the ecliptic and the wintertime wonders and the whole lay of the most of the sky is when they turn south. After I saw the National Geographic map, I thought I'd have to make my own, and I conceived this rectangular or cylindrical projection. And by standing at an angle, of course, you can look at it and see the northern and southern hemisphere stars coming into their own, because just like you see the stretched stop in this street, when you look at it at an angle, it looks right, but then straight on, it looks all stretched out, and that's the way these do here. So you can make this any way you want, but no matter what way you do it on a flat surface, there's some distortion. And celestial globes aren't appropriate because for a celestial map, we're inside the globe looking out, and everything on the globe would be reversed. They have all these globes on sale, but the whole sky is reversed from the way it is on the globe. So that's why we're doing this. And to minimize some of this distortion, our new map is, these maps here are curving with an elliptical top and bottom so that the stars point up to the north and the Little Dipper curves around. And, this is uranography, graphing the universe. Okay, this is the area, what they call the wonders of the wintertime sky. You see Orion, the brightest star is Sirius, that's pointing down to it, Orion, the belt stars, and Capella on the very top, and Castor and Pollux, Gemini, the twins. And the belt stars of Orion point up to Aldebaran, which is the eye of Taurus, the bull, and the Hyades, which are the half-sisters of the Pleiades, right at the, just above it there. And all these stars you can see tonight in December coming up. They come up early in the fall in the early evening and then stay out all winter. But in the summer, if you get up in the middle of the night or toward morning, you can see them then too. And then this is the ship Argo that carried Jason and the Argonauts. It is now comprised of 3 constellations, which the Astronomical Union broke it up many years ago because it was so big and unwieldy that when they were getting to dimmer stars than what you can see with the eye alone, they couldn't manage the numbering, so they broke it up into Puppis, the poop deck, Carina, the keel, which has Canopus, the second brightest star, and Vela, the sails of the ship. And just above it, Pyxis, or Pyxis, is Latin for box, but it means the ship's compass box, or it also was Molus. It used to be part of the sails of the ship. The mast, Molus, the mast. I mentioned that Count Fabriano would appear, and he has finally made it. And we were talking earlier about the marbleized and planetized star map, this pointing up the fact the universe is in motion, that nothing is standing still. And we've captured the galactic flow in the star map and the liquid flow in the marbling, the old bookbinding craft of floating oil paint on water. And here with me is the master marbleizer, Count Fabriano, Cove, his real name. And he's been marbling. How long have you been marbleizing?
Oh, 10 years now, 10, 15 years.
And you primarily do it on fabric, but you can marbleize on any medium, cardboard, glass, metal, whatever, and different pigments. This is an oil-based paint. And he is now compiling a book about not only marbling, but the whole aspect of the flow of everything, the flow of the liquid, the flow of
the wave theory through space.
Wave theory, but in the sand, in the in rock formations,
right, exactly.
In wood,
right.
And you know, we don't deal in astrology at all, but the stars have surely affected my life because here I am graphing them, and other nuances, you know, the full moon and all that. But tides, there's tidal waves. You know, the tides, the gravitational force of the moon and the sun affect the tides. Well, there are also tides in the air, ripples in the air,
and vortices in space
right.
That will eventually will be traveling on, using the magnetic forces to travel on the waves, which are basically represented on our artistic statement of marbleized star maps.
Yes, well, I have my theory about that is that all the gravitational forces meet like in a jigsaw puzzle, and that you'd ride along the edges of the jigsaw puzzle. You know, you control the forces of gravity
the
that were
the interface.
That's right, and that's the way you'd have to move through it, or you could cut straight through it.
Well, that's how basically marble, the separation of the color in the marble is done by density, and that there is a density interface between each of the colors, and as you float the oil paints on top of water and you propagate a wave through the liquid, the wave goes through, and what you're seeing is basically another map. If you had a universe and you cut it in half, in 4-dimension you cut it in half, and you look down on it and made it into 2-dimension, then this is what it would be. It would be a map of the motion that you have, so that we're combining two maps, an instantaneous map of time and a galactic flow.
Yeah, and while you're talking, maybe they could cut in that motion, the actual marbling. We have video of the actual marbling process in hand. Show them your book here. This is your book that he has that tries to describe the whole deal of wave. Here's weather, the waves in the weather.
Exactly, a wave formation. The fronts are basically a vortice of a 3-dimensional vortice. What we're talking about is a 4-dimensional concept of a 3-dimensional model represented in 2-dimension, very flat. Goes from, very simply, right, arbitrarily, from weather to a galactic flow. As you see here, there's different representations of galactic flows, including 2 galaxies meeting on different planes, and this is a weather pattern and a theory of ellipses within ellipse.
Now, I attended this symposium in Aspen of theoretical physicists who were trying to describe mathematical formulas that cause like vortices and suns and things like that. But Confabriano here can throw out anything you'd want. He can actually, his art has developed to such an extent over the years that he is able to tell you what kind of a wave you're going to get just by his throwing it out, waving it, and blowing it with certain things. And I thought maybe by digitalizing and using the computer, it could analyze and solve all these theoretical mathematicians' problems instantaneously, because they're trying to get a formula to say, why does this act like this, you know, and why is this
We have the working model right here. This is the actual working model of all wave theory possible.
Well, there's so much more in this book.
Yes, look at it. See, the art of marbling has started who knows when, but we have examples from Germany in 1500, and it goes back to Japan in 900. Oh yes, here. This is when
Jupiter.
Jupiter, right? Exactly. 5 years before Jupiter came out, this was a representation of a planet with a moon coming across. And as you see, the patterns which are created are actually what we saw later on when we photographed Jupiter. It's an amazing process. And we'll find now that as we get into space, as we get out to where David is charting the map, you'll find that space itself is made of vortices, and that not that the planets are the surface of the planets reflect the same marbling process, but the space around it are overlapping densities of waves. And this is what the marbleized star map. Do you remember the Star Trek convention when we hung huge 20 by 40 pieces of that?
We had the whole ballroom of the Oakland Coliseum, or the Oakland Auditorium. That's what it was, the Oakland Auditorium. He had 14-foot square marbleized fabric pieces, and we did this all. We built a tank out of plastic and out in this yard, and threw you just threw the marbling right on, and.
Here's a piece of cardboard coming through. This is a match, and as you wave the cardboard through the match, the vortice of currents are reflected. And these other black and white photos are from a book called Creative Chaos, where all water is represented through this wave theory. And it goes on. There are people all over the country doing this marbling. And here's a girl from Santa Fe, a particular art of hers. And this is what I'm doing now, is collecting and visiting places where it's being done. It's being done on pottery, on balloons.
And this is an ancient process. This
Ancient
marbling
process.
has been going on. How long is it? Give
No one
us a
knows.
rough
So
history.
like I say, the most recent idea that they have evidence of it early in Asia in 800, but most
Well, you see marbling in your coffee. You know, you see the
exactly,
stuff
yeah.
rolling out of
The oil on top of a puddle as you cross the
Right,
street.
right in the gas station.
A glaze on top of pottery,
Yeah.
or a super ball. you
And
know?
the interference diffraction phenomena that's caused, like when you see the shimmering ahead or over the radiator, the thing, and it's
Combing. What you're talking about is combing. You lay down, you start a pattern, a very symmetrical, coherent pattern, and with the use of a comb, small wires, you can create patterns such as this peacock combing, as I grabbed from your table. And another interference would be as if I had straight lines of these color and then blew air from the top. The Arab word for this is called wind and water. So you have the water and you have the force of the wind.
when a car goes by a window, and you can see reflected on the other window almost all the grains of the glass on the wall.
The moire pattern, reflected moire pattern.
Well, no, I see a grainy substance, but I'm getting out to the shadow band phenomena in solar eclipses. When there's a total solar eclipse, just before and after totality, the air begins just like it's shimmering, just like when you see the light diffracted through the radiator. And superimposed on this shimmering are light and dark bands, flowing bands, sometimes spaced wide apart, sometimes closely apart. It's like a wave that comes up on a beach and goes away. Etched in the sand are these little ridges, you see. But sometimes there are ridges going over ridges, and wherever the nodes meet, then it cancels it out. Like the two wires on the wherever they cross, it looks like there's nothing there. There's and the classic experiment is where you have a light bulb behind a flat board. You put one hole in it or two holes in it. The reflections on the wall
polarizing of the
will
light.
all be disappeared when the thing. And that's all interference, diffraction, and this is the flow of it all.
It's
and
the
here
key
we
to the universe.
Right.
Right,
And thank you.
before you go away, I've always wanted to do this, to be on TV.
No, it's gone.
No, it's not a flash. I won't burn out. I've always wanted to do this. That's amazing. I'm photographing you. Who's behind there? Originally, this book that I'm doing, a research book on marble, was intended as a special effects presentation for Carl Sagan and his TV show. And David and I went down to Los Angeles, and we set up a marbling tank right on the street in La Cienega, and did this marbling on the street where we would marble, and we videoed it. And along with it was this presentation, this book of explaining the art of marbling. Marbling may be defined as the art of arranging moist colors on an elastic surface that they will either or can be made readily to assume fantastic sundry forms. Such colors being transferred onto fabric, onto paper, onto books. It's been used for years as end pages. David was my #1 assistant when we would print in Berkeley. Oh, here's a wonderful example of an overlapping moire of marbling going over on top of marbling, and the flipping of it, making it anti-symmetrical. I was just saying how David W. Teskey of Manchester, Iowa, has more copyrights on the heavens than anyone alive, and I've heard him say that he actually owns the heavens. Since he has copyrighted the image of the heavens, and no one else can use the image, that he is being blasphemous and saying that he owns the heavens.
Nobody can come to the heavens but by me.
That's right. Every time everyone looks at the heavens, they owe you, right?
Right.
Well, I'll tell you an interesting story about copyright. If you think that you can use this image, David Teskey sold to the Oakland Museum star maps. They took a star map and removed the names, used 1/3 of it, turned it upside down, and created this, basically what most people would think was an abstract dot pattern. Well, David's walking down the street and he sees this dot pattern as a background for a poster advertising the Oakland Museum's concert series. Well, knowing the stars, he realizes that this is his image, and he sues the Oakland Museum for copyright infringement, and I think it cost him $1,200 or $1,500 a sue, and you won $1,200. Is that what it was?
No.
It was something